Well, let's start with resistance. What is resistance? Resistance is the property of an electrical component to resist or to oppose the flow of current or to oppose the flow of charges. The SI unit is ohm, and the symbol for ohm is omega. As you can see it here in brackets. So some materials have very little resistance. Okay, let me write it here. Less resistance. Okay, a material with less resistance is a good conductor. Good electrical conductor. Very little resistance. Good conductor. E.g., the examples are copper wire, which is the one that we use at home for connecting electrical components. That's it. Then we also have materials with very high resistance, say very high resistance, very high resistance. These are called insulators or poor conductors. Poor conductors are known as insulators. They are called insulators, right? And they are used for resistors. They can be used for resistors. So now let's look at the factors that govern resistance. The first one, say number 1. Let me start on a new page. Let me find a new page. Yes, here is a new page. So what are we saying? We are talking about factors. That is factors affecting resistance. So resistance depends on this function. Factors, right? So it's a function of these factors. It highly depends on the factors. So the first one is length. Okay? Length. So resistance increases with the length of the conductor. So I omitted T here. It increases with length. So here we are in increases with length. It increases with length. Okay, let me try to draw two conductors. What can I use? Yes, here are the factors affecting resistance. So resistance is dependent on them. The first one is length. What we are saying here is as length increases, resistance also increases. So the resistance increases with length. So as length increases, resistance also increases. So we have wire A and wire B. Everything else is the same except their length. So the shorter wire will have, what is going on really? Not happy with this at all. Okay, the shorter wire, which is wire A, will have less resistance. Then B, which is longer than A, will have high resistance. So that's how resistance is dependent on length. The longer the wire, the higher the resistance. The shorter the wire, the lower the resistance. That's it. So let's look at number 2, the thickness of the wire. So we have C. C is thicker than D. So how does resistance respond? When the wire is thicker, the resistance is low resistance. Then for D, since the wire is thin, the resistance is high resistance. That's it. Then how about the material? The material used to make the conductor. We are saying iron has more resistance than copper. That is when everything else is the same except the material. Same thickness, same length, same temperature. Right? So, but we know that copper is of high resistance compared to what? Compared to gold. Yes, as much as we want to be, using less energy, right? Less energy and saving money for our homes. Let's look at the factor number 1, length. When the socket is 1 meter from your microwave or refrigerator, you cannot be found using a cable of 5 meters. No, it's not a good thing to do because it will have a high resistance. And when the resistance is high, that means you are paying more money for your utility bill for nothing, because most of the energy, electrical energy, is going to be converted into heat. It's going to heat up this wire, and you are not supposed to be heating the wire. You want the electrical energy to work where it's needed, right? So you should always choose the shorter wire where possible, right? Then number 2, thickness. Yes, you want to choose the thicker one, which has low resistance, but it depends on a lot of things. Really. And then I think it could be more clearer here. The material used, yes, we choose copper because it has less resistance. We don't want iron. But gold has less resistance than copper. But how many people would use gold really? For wiring your house, can you really use gold? For some of us, we will end up having the gold used in the wires for conduction, for wiring. We might end up having them being valuable more than our house. And it doesn't make sense at all. It doesn't make sense, right? It doesn't make sense. So it doesn't make economic sense. Sometimes we consider a lot of things, right? So that's it about these three. Let's look at the last one, which is temperature. Temperature. What are we saying under temperature? We are saying for metal conductors, resistance increases with the rise of temperature. Why is it so? Okay, the reason is that when you have your metal being heated, what happens is the atoms will gain kinetic energy, and when they gain kinetic energy, they vibrate vigorously in their fixed positions. So as they vibrate, they are going to clash with electrons. They are going to collide. The electrons want to move from one point to another for electrical conduction, but now they are now colliding with atoms. So there are now more collisions because there is no time when they are at rest really. But we are saying they gain kinetic energy and then they vibrate more vigorously. So the vibrations increases. Okay, let me just give you another example. So maybe say you are at a, what can we say? Maybe some party, right? Yeah, during your birthday. And there are a lot of people there. They are seated. You are giving them food. Maneuvering between your friends and whoever is invited while they are seated, you can easily go through them, washing their hands, giving them the snacks or food or whatever you're giving them, right? But when now it's time for dancing and they decide to dance, going through them will be much more difficult because while you're passing, they're dancing, they're moving from one point to another. So it becomes difficult. So that's exactly what happens with electrons. They're colliding with now or more vibrating atoms or atoms with more vibrations. So kgang ya me ke clear gongwe ka Setswana ka re ba bangwe ba ra ba tlhaloganya. Kgang ene ke e bua ke gore ha o le ko clubong go na le ba tsamayang di club a ke re gone la is ko clubong kana ko partying or wherever a ke re Christmas party a re tsaya club is for ke rata di club but ko clubong wa itsela gore ha ka re gongwe kana mo club ke rata batho ba eme ka maoto ba bina maybe o bona motho kwa batla go mmitsa wa tswa go motswela go gongwe wa go tsana go eterile go tswa gone ha o leng teng wa gore ga go motho la go se kgakala because batho ba le ba ira they are dancing ba bina go thata gore o hitana mo go bone especially ga o ka tsena pine mo natong wa re ya ga makhatsi o ta bona story batho ba tla ba binisa makhatsi ya minke ra hela gore la ile ka hela go tsena pine ba e rata mo le mo a tola go ra sentse ro mo ile go jele ma get down wa emela gore go a thula o tlo tsana go etile go a go gore ga go batang go ati la ile gore batla go countering wa go reka wa go tsana go etelele mara ha pina ka ema anya o iphitela hela senta gona mathata so di electron le tsone di kopana le yone mathata gore ha di re ja tsama ha temperature ya go godimo di atom di nna excited thata di gain kinetic energy be di vibrate thata di move okay, from side to side in their fixed positions. So moving on to B, semiconductors. With semiconductors, the resistance decreases as the temperature rises. Why is it so? Okay, semiconductors, those are materials which are between conductors and bad conductors or poor conductors, which we call insulators, right? Or maybe I can just write conductors. We have conductors here. We have poor conductors, which we call insulators. Because I wrote pure, let me just write good conductors. So in between here we have what we call semi what? Conductors. So they are in between. So what really happens when the temperature rises is, now the electrons, they get excited. We say they get excited, or they just gain kinetic energy. And when they get kinetic energy, they are kind of able to break through from their outer shells, right? To be able to now move, because as you know, metals, they have free electrons. Pure conductors, they don't have free electrons. All the electrons, they are bound to their shells. But as for metals, no, they can just move around as they want. So semiconductors, when they gain heat, when they are heated, what happens is those electrons, they're kind of able now to break away from the shells which they were bound in. They are now able to move. They are now free, like in metals, because they gained kinetic energy. So now a semiconductor is kind of approaching to be a good conductor. So that's the reason, right? So that's what we are saying. So to summarize, the factors affecting resistance, number one is length. As length increases, resistance also increases. Number two is thickness. The thicker the wire, the less resistance it has. The thinner the wire, the more resistance it has. Then the material used. Some materials have less resistance, while some have high resistance. And temperature for conductors, as the temperature goes up, resistance also goes up. For semiconductors, as temperature goes up, resistance goes down. So that's it about the factors affecting resistance. Now let's look at the types of circuits. So the first one is a series circuit. A series circuit will look like this. I really wish I could use this. Types of circuits. The first one is series circuit. Here is our circuit. So as we can see, there is only one part. When there is only one part from positive terminal to negative terminal, we call that a series circuit. So there is no any other way. Each and every charge will flow on this part, or current will flow on this part. So this is a series circuit. One thing that we need to make clear here is the idea of the direction of current. So we are using a conventional current flow. This one is called conventional current flow. This is one that we're going to use, but it has since been noticed that it's not actually the positive charges that flow. So it's supposed to be the negative current flow, this one. But because the scientists in the past, they thought it was the protons or positive charges flowing, it was later found out that no, it's actually the electrons. But because of convenience, we are still using this conventional current flow because everything else works well when we think of current as the flow of positive charges, as if it was positive charges flowing. But anyway, we are not going to be talking about the electron current flow, right? It's just for convenience. It's just for convenience sake. Nothing much. Nothing much. Let it go. It has to go. It has to go because nobody needs it. I just wanted to make you aware, right? So that's it. That's it about the conventional and electron flow. Now we want to look at the facts. The facts. Let me cut here. Those are the facts about series circuit. About series. Oh, what am I doing? Circuit, right? So the first thing that we want to look at is the current. The current, guys, the current, right? Current. So if we have a circuit like this, we're gonna have ammeter 1. See, ammeter number 2. Ammeter number 2. Let's have a bulb here. We can't have a circuit without any components. So the reading for ammeter 1 is the same as the reading for ammeter 2. So if this is the direction, right? This is positive, this is negative. So this is I1, this is I2. So we are saying the reading will be the same. And remember that the charges or the current cannot get used up around the circuit, right? It cannot happen. The only thing that gets used up is the energy. Okay, the idea of charges moving around the circuit is just like yourselves. Supposing you are from the same house, maybe there are 4 of you, or even say the whole school. If the number of students who entered at the gate in the morning is 700, right? After school, the students who are supposed to be seen going out at the end of the day, the total should be 600. Yes, you might be hungry, you might be what, but I don't care. The number has to be the same. So same applies to current and charges. Let's just talk about current, okay? The current at this point is still the same all the points along the circuit because there is no other way around. There is only one part. So I1 is equal to I2. What is current? Is the flow of charges per time. So that's it. The number has to be the same, right? So never think current can get used up. It cannot get used up, right? That's it about current. Now let's look at resistance around a series circuit. Yes, the new page. Let's look at resistance. Okay, to remind ourselves that we are talking about series circuit. Shouldn't forget there is a parallel circuit, so it is crucial that we distinguish between the two. I don't want anyone to get lost. Here is our circuit once again. What we have here? We have a resistor number 1, resistor number 2, right? Maybe this way. Yes, remember, negative, positive, direction from positive to negative, conventional current flow. That's it. So this is resistor number 2. Then the resistance, the total resistance we can call it RT. Oh my god, let me write it in French. RT4, total resistance. How many resistors in series? There are 2, so it's R1 plus R2. So let's give them values and see what we mean. 2 ohms, this one is 2 ohm, this one will say is 5 ohms. So resistance, equivalent resistance, or total resistance. So it's R total. Okay, this T is not really standard, but I'm just doing it so that we remember that this is the total resistance. Total resistance, R1 plus R2. What do we get? 2 ohms plus 5 ohms. So RT will be 7 ohms. This is how we do it. So this is our EMF, right? So how about the voltage? Let's look at the voltage. Voltage. I think we should go to a new page. Page 10. Good. So with voltage, this is what we are going. Let's remind ourselves, series circuit. We shall not forget voltage. We are looking at voltage. voltage, right? The first circuit, okay, let me couple of cells. What do we have here? We have some resistor. Okay, let's go up to here. And then we can have a bulb, right? We have a bulb here. Then all the way up to here. Then we have, so the current is flowing, as you can see. The current is flowing because the switch is closed. You can say the switch is here. Then this is the positive terminal, this is the negative terminal, right? Yes. So what we know, a voltmeter is used to measure voltage, right? And it is connected across the component. Even when it's removed, current will still flow. So it is not part of the circuit. Already the current is flowing. This bulb is on, right? So what is going to happen now? We bring our voltmeter. Let me draw it nicely here. V, right? That's V. Then we connect it this way. So this is voltage. This is the potential difference between this point and this point. Then we connect another one here. Let's just connect another one here for convenience. The space. Yes, V. Right? That's it. Supposing we don't know the value of the EMF. Right? We didn't check anything. We just connected these two voltmeters. And this is, call it V1, call it V2. If V1 is 10 volts and V2 is, say, 15 volts, say 15 volts, V1 is equal to V2 is equal to. So, what do we know? We know that a charge which left the positive terminal, each charge, let's talk about one charge. Let's call it the test charge. Whatever happens to it happens to all other charges, right? So the charge leaving here at the positive terminal, it goes around the circuit with some voltage. It has some voltage, right? It goes around, and the voltage it has, let's call this point X. Let's call this point, oh my God, see what is just happened. Well, problem fixed. So this point, call it Y. Then we can call it Y. So at this point, it should have the maximum voltage. It should be the voltage that it got from the EMF. I mean the source, which is called EMF, right? So it's the source voltage that it has here. At Y, it should have 0 volts. So it should use all its voltage. Because here is 10 and here is 15. So it used the 10 and it was left with 15. When you combine them, it's 25 volts. So that means it was given 25 volts. So the value of EMF is therefore 25 volts. So voltage, that is the voltage from the source. EMF. We don't like writing EMF. We just like writing V for voltage. Like I said, EMF is also called voltage because it's the source voltage. So voltage is V1 plus V2. Therefore, the voltage is V1 plus V2. Inserting values, 10 volts plus 15 volts. Therefore, V is equal to 25 volts. See, that's how it is. So this is voltage in a series circuit. You just add them. So let me give you another example. Here is another example. I like to call this B1 for bulb, right? Then this one is B2, bulb number 2. So what we have here, yes, this is what we have. But remember, if you're drawing circuits, you should use a ruler. These are supposed to be straight lines, but I'm just trying my best. But I could use a line, but it will take time. I don't want to waste time, my friends. So supposing we have 20 volts here as the value given, and we are told B1 is oh my god, see, need to change something. Identical to B2. What it means is their resistance are the same. The resistance is the same. That's why they say B1 and B2 are identical, right? So what does it mean? It means for each and every charge leaving the power source with some voltage of 20 volts, it's supposed to divide that voltage equally, because the work it needs to do, why do we say so? Because each and every charge that leaves the power source, each and every charge is going to pass through B1 and B2. So because they are the same, they are of the same resistance, right? The difficulty for the charge to pass through them is the same. So the charge is going to use equal amount of voltage in this bulb and in this bulb. So in that case, it will use voltage of 10 volts. And here, call it V1, call it V2. It's going to be the same, 10, 10. I hope it does look like a 10 is this one. As we can see, the voltage is shared equally because they are identical, they are the same. So once again, so you see that if you are given the value of EMF, you can predict or you can determine the voltage for the voltage across the components, right, in series circuit, as we have determined earlier. V is equal to V1 plus V2, that is in a series circuit. Never forget that. This is in a series circuit. Okay, another example. Let's do another example. Take another page 11. I'm going to write once again series. We don't want to forget that. Series circuit, right? That's what it is. Series circuit. Series circuit. Here is our circuit. the power supply. What do we have here? We have a resistor, then we have another resistor here, then we have another resistor here, goes all the way to this point. Why did I make them 3? It should have been 2. Should have been 2, but that's okay. Say this is 2 ohms, 2 ohms, 2 ohms, right? And the value here is, what value can we choose? Say 15 volts. Each and every charge leaving the positive terminal, it will be having 15 volts, and there are 3 resistors of equal resistance. So the difficulty of a charge to pass through these resistors is the same. Therefore, they are going to share the 15 volts equally. So this will be, call it V1. That is the what? The voltage drop. The voltage drop will be 5 volts. Voltage drop 5 volts. Good. At this point, the charge will have 15 volts. At the end, it will have 0 volts as a requirement. Now, let's look at another example. I hope at the end you will have understood. And remember, the questions now, they will definitely combine a lot of things, and you will be required to calculate all these quantities that we've been talking about. It won't be just simple as I'm doing it here, because you will have current involved, voltage and resistance. So your best bet is to pay attention. So let's say this resistor has a resistance of 2, and then this one 4, and the voltage here, let's say the voltage of the source is 6 volts. I think 6 volts, it's okay. So each and every charge leaving the positive terminal will have a voltage of 6. At the end, as it approaches the negative terminal, as usual, it will have 0 volts. It will have 0 volts. And what did we say? We said for voltage, really, remember, voltage, if we are talking about one charge, is the energy, right? So each charge is given 6 volts, or each charge has 6 volts. It's not given 6 volts, it is given 6 joules. So as we can see, the amount of energy is gonna use to pass through this resistor is twice the energy that is going to be needed to pass through this resistor. So what do? We look at the ratio of resistors. 2, 6, right? 2, 6, 2 into 2, 2 into 6. That is, the ratio is 1:2. The total of 1 and 2 is 3. So we have 1/3 and 2/3. Call this one R1, call this one R2. So R1 will take 1/3, R2 will take 2/3. 2/3 of what? Of the energy per charge. That's it, that's voltage, right? So voltage for R1 will be 6 times, but it has to get less because it is not as difficult as 4 ohms, right? 1/3. 2 into 2, 1 into 6. Really, is this correct? Yes? Yes or no? 3 into 6 is not 3 actually. That is 2. Then 2 times 1 is equal to 2 volts. So the voltage here is 2 volts. The potential drop across 4 ohms resistor, that is for R2, will be total voltage, but it is going to get 2/3, right? 3 into 3, 1. 3 into 6, that's 2. 2 times 2 is equal to 4 volts. 4 volts. That's it. As you can see, 4 volts is double that of R1, which is 2 volts. I don't know, I have 4 here, I have 4. There are some students who might really get disturbed by this. I don't like what I see. But in that case, then I'll bring on another circuit to make things clear for them. I don't want to confuse anyone. So this is R1. I don't want anyone to get confused here. So this is negative terminal, this is positive terminal, this is R2. Supposing the value here is, what can we say? We're just going to double this. 5. Let's say 5 ohms. And this will be 10 ohms. Then I will choose 60 volts. 60 volts. And then let's calculate as before. V for R1. We can see that 5 is half of 10, 2 is half of 4. So the ratio is still the same, really. You can follow the steps here. You'll find that is the same. So I just want to clear this. I don't want to confuse anyone. So this, we go on and say 60. R1 is less than R2, so it will get less. Therefore, it's a third. Yes, it's a third, not 1/2. 3 into 3, 1 into 6, 2. So this is 20. This is 20 volts. So V R1 here is 20 volts. So this is the answer. But when we get here, is there any need to calculate for R2? Because 60 minus 20, that means it's 40. But anyway, let's just do it. R2 is equal to 60 times 2/3. That is, as before, 20 times 2 is 40. So VR2 is 40 volts. And one important thing that we need to notice is, because this resistor is double this one, it is definitely going to get double voltage compared to this one. So if this one, if we change the value here, if I change the value to whatever value I like, or even if you are told that this voltage is 100 volts, definitely you have to know the voltage here, because if this one gets 100 volts and it's 10, this one is half of this, so same applies, the voltage will be half of this, that is 50 volts. Therefore 50 plus 100, it's 150 volts. So if you understand this, your life will be much easier. Even before calculating, you can know, you can tell. And if you make a mistake, you can easily tell that, no, I must have made a mistake here, right? So that's what it is. I think now we should look at the parallel circuit. Parallel circuit is a little bit complex, and we might as well need a new video for that, because I don't like my videos becoming too long. So guys, let's meet in the next video, where we'll start by looking at the parallel circuit. Thank you guys. So follow me. Let's go there right now.